Okay, so we had the review today, and then I polled a bunch of the class on your knowledge of the force method. So either you definitely haven't learned this, or you've all managed to persuade me that you haven't, and that's fine. So we're going to go through this fairly quickly, the force method. So we've been through what static determinacy is. You guys are pretty good on that. So there's different means that we can solve a structure if it's not statically determinate. And one of the simplest, one of the easiest ways, if it's got a degree of indeterminacy of 1, we can use the force method. So we're going to use that because it's a really good vehicle to show why using work energy methods are useful. So I'm going to draw the same problem we had before. Also, I realized, let me go back to, this is the lecture that I just went through. I realized I never actually answered this problem here, but I'm going to leave this up and I would like you guys to solve this. We're going to actually produce all the equations to solve this today, but I want to just skip over that, and I'd like you guys to produce that and maybe send it to me on Slack if you manage. So what we're going to change is I'm going to have the same problem. Everything's exactly the same except for we're going to have 2 built-in supports. So we've got a force of P, we've got A, A, B, and C. I was just checking I've got those in the right order, A, B, C. And this now means we've got 4 reactions. So we have FAY, FBY, FBX, and FAY. No, FAX even. So we can see that this problem is externally indeterminate because we've got 1, 2, 3, 4 reactions, and we only have 3 equations of equilibrium to solve the structure, or solve the free body diagram. So one of these is what we call a redundant reaction. Okay, one of these is redundant, which means that we can take it away and the structure will stay in static equilibrium without that reaction being there. So we're going to pick one to be our redundant, and it doesn't actually matter what you pick for this problem. We can pick any of them, and I'm going to choose to pick this one right here, FBX. The reason I'm choosing this, hopefully is obvious, is that if this is my redundant, we've already solved this problem using these 3 supports. So the step that I'm going to go through the steps that we utilize for the force method. 1, which is pick a reaction to be our redundant support. Redundant support or reaction. I'm sort of using those terms a little bit interchangeably there. So this redundant one, we now are going to change the value of this a few times, and we're going to move the structure around, and then we're going to, using the numbers that we get out of this, determine the actual value of it. So the way I'm describing this is a little bit roundabout, but our redundant one is now going to be FBX for our problem. And I've already sort of described this at the top level. We want to see what happens to the structure if FBX isn't there. We then want to see what happens if FBX has a value of 1, and then we'll see how small a value, how many times too small is a value of 1. And I'm going to talk you through the steps of how we achieve that. So FBX then becomes a known for this problem. Unlike FBY, FAY, and FAX, which are unknowns to be determined, FBX becomes a known in the problem, even though we don't know its value yet. And what do I mean by that? I mean that it's then a force that we can apply in our free body diagram. So we would redo our free body diagram subject to a loading of F and FBX. And when I say the value is known, it's either going to have the value of 0, 1 or -1, or the value that we're going to determine, which we'll just say is FBX. And this is going to be the value that we're determining. And once we've got that, we then solve the whole problem again with that now being a known value. So we then do free body diagram to determine the 3 remaining supports as a function of both the applied loading and the redundant reaction. And I'll go through and I will do all these steps, and I'm just going to talk you through the steps that we're applying. Once we've got all of those, we then do the same thing. We do the method of joints. And we've got to include FBX, or the redundant reaction. Let's just rewrite this up here. Put the 3 reactions as a function of those 2. Let's say that we've got R as a function of P and FBX. Previously, when we did the method of joints, we said we're going to do the method of joints, and I then ended up with the internal forces as a function of the reactions, which we've got here. We now need to do it again, so we're going to make it a function of all 4 reactions. So the 3 that we would have determined from the free body diagram, and the 1 whose value is known, it's either going to be 0, 1, -1, or the value that we solve at the very end. And this will become clear once we go through the whole thing. Okay, so this is my internal forces, and then going to be a function of those reactions. And this includes the 3 that we've determined from up here, and then the 1 that's unknown. Or the one, sorry, not the one that's unknown, the one that's redundant and has whatever value we've decided. Okay, so once we've gone through that, we're then going to determine how much the structure moves in the direction of the redundant reaction. Okay, so if the reaction's not there, we're going to say, okay, let's say, before I say determine how much it moves, we'll set the redundant equal to 0. And then we determine how much it moves. Okay, so we're going to end up with some value for how much the structure moves in the direction of that redundant reaction, which we've set equal to 0. And we're going to call this big delta. And for this problem where we've set the redundant to be Bx, then this would be delta Bx for this case. Okay, it's going to be a numerical value, or it might be a function of the Young's modulus, area, and L. If we don't know what those values are, those would just be variables in the problem. So once we've got this value here, if it turns out this is a positive number, i.e. the structure has moved in the direction that we've defined as positive on here, then we want to see how much, well, if the structure moves in this direction, then we know the reaction must be pushing in this direction. If conversely the structure moves inwards, which it's not going to do with this load, then we know that the reaction has to be pointing in this direction. So that then tells us the sign of the unit force that we want to apply. And in fact, it doesn't really matter the sign of it. We can apply a unit force of 1 and we'll get all of the mathematics balances out anyway. So this bit here is just a good way to think about the structure. You can apply a -1 if you want. If we apply a 1, as long as we take care of the sign of the next deflection we're going to determine, then everything comes out in the wash and everything's fine. But so we get delta bx, we've got this. This is how much the structure moves if the support isn't there. Okay, and we can think about this now. So if this is my structure, and there are FAX, FAY, FBY, and I've got FBX, and I've set this equal to 0. What these reactions are doing, FBY is stopping node B moving downwards. Okay, FAY is stopping node A from moving downwards, and FAX is stopping node A from moving to the left. Okay, that's assuming these are all positive values in here. FBX is stopping the structure moving to the right. Okay, stopping the structure from moving to the left in terms of a positive sign here. So if we apply our loading and set this equal to 0, the structure is going to move somewhat. So let's say the structure moves in this big exaggerated loading to something like this. Okay, this distance that we would have determined is defined in the same direction as the redundant reaction. This would be delta Bx. Okay, so we know that without that reaction there, that's how much the structure is going to move under the applied loading. So it follows that the actual numerical value of Fbx when we've got this loading is just enough that this displacement isn't happening. It only has to be the exact size such that this displacement doesn't happen. So we're going to assume that the structure is linearly elastic, and it's sort of linearly elastic, which means that if we need 10 newtons to move a certain distance this way, 10 newtons will move it the same distance the other way. So let's draw this up here, for example. So if we find out that a structure moves to the right, then we would know that our force is working in this direction. So we then say, okay, Fbx must be equal to a negative number. Let's try it equal to -1, for example, and we'll see how much this second displacement is here. This is the small delta. Sort of haven't explained that particularly well there. Let's go back over here. So because I've sort of jumped ahead a little bit there. So we've set the redundant, we've worked out this delta Bx. Let's say if delta Bx is positive, so if delta Bx is positive, then it means that the structure has moved in the direction of delta Bx. Therefore, Fbx has to be a negative number. Okay, it has to be a negative number for that to be the case. If delta Bx is negative, And conversely, FBX must be positive. And that makes sense. It's got to be there to overcome whatever the movement that would occur if that reaction weren't there. So we then apply a unit load in the direction of these forces. So what I said about not applying a -1, we should really apply this as a 1 or a -1 in accordance with this sign convention here. You can apply a 1 and just be careful about signs, but let's just apply a -1 for good sense. So we'll say apply FBX, which is our redundant reaction, equal to a unit load in the direction of its known direction. And then we determine how much the structure is going to move back, which is this small delta that we've just determined. So when we apply this, we have no external loading. So for our case, P is equal to 0. And then from here, we work out this small delta. We get delta Bx. That's then the amount the structure moves back under that unit load. And then it follows that for the condition of no movement, that's the ratio of this divided by this gives us the actual value of FBX that would give us no displacement. Because if these two are equal, then we know the reaction has to be 1 Newton. Okay? If this one is 1 meter and this one's half a meter, then it tells us the reaction's got to be 2 newtons, for example. So the actual value of the reaction is given by FBX is going to be equal to delta Bx divided by delta Bx. Okay, and if I'm being careful here, then the sign of this bottom one should be negative. Okay, so I would get a negative value in here. Okay, so that's the theory here of how we do this. The application is going to be how we prove this and how we go through it. So we'll go through it for this simple example here. We've already said that this one's going to be the redundant. We need to just redo the free body diagram and method of joint, and then I'm going to put it all into Python and show you we can tidy this up a little bit, how we do these sort of repeated systems. So this step here, we've picked our redundant reaction. What we've effectively done with this step is we have turned our indeterminate structure into a representative statically determinate structure. Okay, which I'm going to say is RSDS for short. Okay, so we've got that. These are, in fact, all the way down to here. These are all on the representative statically determinate structure. Okay, so we've gone through that, and we're then going to just be solving now a different system. So we've worked out how much the structure moves if it didn't have that reaction. We then say, okay, I'm going to set this equal to either 1 or -1, and then we're going to solve a different set of systems here. So we've worked this out. This is with no load, except redundant. And then this last one here is the real structure. And for a real problem, once you've actually solved this value here, you then need to put it back into free body diagram method of joints to work out what the reactions and the internal forces are when we've got both this and the applied load. So let's go through it. We've got the equations for the free body diagram and the method of joints from before. I'll redo the free body diagram and then we'll just amend the method of joints. So for our free body diagram, we've got P. I'm going to put F, B, X. Let's just write the node numbers or the node indices. Now I've drawn these in different colors on purpose. So the blues are the things that we're trying to determine as a function of the red things. FAX, FAY, FBY. So for the sum of forces in the x direction to be equal to 0, we've got P plus FAX plus FBX is equal to 0. So FAX is equal to minus P minus FBX. So we've got that one sorted. There's nothing else vertically, so these two still have to be equal to, well, one's got to be equal to the minus of the other. So we solved that last time. I'm not going to write down everything. Say FAY is equal to minus FBY. And in fact, we should be able to see that if we evaluate moments here, we're going to have the same value of these two as we had previously, because there's no means for FBX, which is now this extra term that we've got in here. There's no means for this to provide a moment, either at B or at A. Okay, so let me just get those two from before. We had all the way up here. Okay, we had FAY was minus P root 3 on 2. And then FBY was equal to P root 3 on 2. So we've got our three terms for the free body diagram. Let me bring that one there and that one there. So actually these two are the same. This one has changed. We then need to look at the method of joints. Now the only joint that's going to change with the addition of this is node B. So we need to re-look at the equations for node B. I'm just going to solve node B again. So we've got, I'm going to draw my known forces on. So at this point we know what FBY is and we know what FBX is. We don't know what the force in CB is, and we don't know what the force in AB is. This is 60 degrees here. So for vertical equilibrium, the sum of forces in the y direction has to be equal to 0. So FCB sine 60 is equal to FBY. I'm forgetting what sine 60 is as a surd. What is it? It's root 3 on 2. So FCB is equal to 2 FBY divided by root 3. I've made a mistake here. There should be a minus sign here. Sorry. Let's make a minus sign because it should be this plus this is equal to 0. I'm skipping a little bit of a step there. We also know the sum of forces in the x direction has to be equal to 0, so let's write this out properly because I failed to do that a moment ago. Let's say FBX is equal to FAB plus FCB cosine 60. Cosine 60 is a half, I think. Yep, a half. So at this point we know what FCB is, so we can now immediately get this. We say that FAB is equal to FCB. No, sorry, it's equal to the reaction FBX minus FCB cosine 60, so it's FCB divided by 2, and that's actually minus this, so the minuses cancel and the 2 goes from the top, and we end up with plus FBY on square root of 3. Okay, so we've got that one. Yeah, we've got all of the forces now, so we've got this one here and this one here. So those are this one hasn't changed, this one changes, okay? So we've got 2 things that have changed in our code. So I'm going to actually just go back to my code. I'm going to tidy this up a little bit as well. So because we're going to have to repeat different parts of this code. So this is exactly as I left it. Sometimes if I've been playing around with a bit of code for a long time, I'll restart the kernel, which clears all of the variables from memory. And then I will check that it still runs again. So let's just check, does it run? That's good because I haven't practiced this, so I want to just check that it does still work. So we've checked that everything works and the code is, producing the correct answers. I'm going to tidy this up. I'm going to bring the method of joints subfunction up here. Let's just check this still runs. I'm going to do kernel. I think this button here restarts the kernel. Yeah, let's try that. Okay, so this still works. So I can define my free body diagram on my method of joints up here, and then I only need to do this at the beginning. What I'm also going to do is I had these little bits of code in here which printed out the reactions nicely. So I'm going to take this whole thing, I'm going to cut it, in fact I'm going to include this in there. I'm going to cut this line. This one was for printing the reaction, so I'm going to just define a function called def print reactions. And I'm going to put everything that was in there, it's got to be indented within this function, so it's going to, every time I call print reactions, it's going to print out the reactions and then a new line after it. And I'm going to do the same for the internal forces. Just going to put a new line feed after that. Okay, and then what I'm going to do, I'm just going to tidy this up a little bit. So, and I'm going to cut these out and put them in this cell down here. So when I run this one up here, I can then redo, this is just the same problem as we've done before, nothing happens. And what I can do, after reactions, I'll type print reactions. If I try and do this, I know it won't work because I've made a function. So what I need to do is tell it that it's a function by putting the brackets after it, and it will know that I've already defined that function. It will then print the reactions out for me. And then I'm going to do print forces. Is it print forces? Yeah, print forces was the name of the code. Okay, so this is just tidying this up a little bit. So we'll think about the number of times we need to do this problem. Before we get there, I need to change these functions a little bit. So let's go back to my method of my free body diagram rather. So the only one I need to change is FAX. It's now equal to minus P minus FBX. So first off, my free body diagram at the moment is only a function of the applied load. I'm going to take this reactions out and I'm going to put it as an input into free body diagram, meaning that when I run free body diagram, if I don't give it a reactions, it's going to assume that I don't have it, I don't know what they are. But otherwise I can then supply it with a reactions dictionary. I've also got to then change the value of this one here. So this is f(a)x is equal to minus p, which is what I've got here. I now need to do minus fbx. So I'm going to have minus reactions bx. Okay, that's this change has been put into here. And then for the method of joints, I need to change, it's just FAB then actually, isn't it? Just FAB, because FCB is still the same. It's FAB is equal to, so it's this line here. This is already the bit that I had here, which was FBY divided by root 3. I now need to also include FBX in here. So I've already got reactions here. Plus reactions BX. This is a little bit confusing how in free body diagram I supply applied load and then reactions, and in method of joints I supply reactions and applied load. So I'm actually going to change these around. Actually, no, I'm not. I'm going to leave them as they are because this sort of makes sense the way that I'm applying them. Just be careful that there's a slightly different syntax in the way these two things are called. If I run this, oh, it doesn't like that because so down here it says doesn't like that, and it's because I've used curly parentheses on here. These should have been square brackets. I run that, which just reinitializes those or redefines those functions. It doesn't like this because it doesn't know what value of bx there is. Okay, so when I try and run this, it doesn't have this value of bx to put into it. So I need to now tell it that when I first run this, bx is equal to 0. So let's go down here and let's introduce some headings. I'll say let's mark down. Didn't mean to do that. I want this cell to be marked down. Man, my typing is on point today. Okay, so here we go. So the first system, we set fbx is equal to 0, which gives the representative statically determinate structure. So let's set that value to the reaction. So I've now made a dictionary and I've told it that it's only got one value and fbx is equal to 0. So I've then, what I had previously was in here, we've set the dictionary for the applied load in here. Now, syntax needs to change slightly here. I need to go my reactions is equal to FBD of applied load. I now need to also, I need to supply the reactions to it, or otherwise it won't, otherwise it'll assume the reactions as an empty dictionary, and then it will have a problem when it gets to this point here. So let's put reactions here. I'm going to comment these lines out for now because I want to just see whether this works or not. Doesn't like that because it has. Oh, that's because I've called this FBX here. This shouldn't be that. It should be BX. Okay, it says here key error BX. It's looking for the key BX in this reactions. Reactions has the key FBX, which is me being inconsistent with my nomenclature there. So if I run this, here we go. It's now going to print out all 4 of my reactions, including the redundant. So these are just the same as they were before, but I've got this now, this new one, which is 0. So before I print the reactions, I'm going to put here, print for the representative. Really cannot spell that word today. Representative. Okay, so we've now got all of those reactions. We can do the same thing again with the method of joints. So we've got our function method of joints, and we need to supply in the order here. It's reactions and then the applied load. So let's go here. In fact, it doesn't need that applied load. No, it doesn't actually need that applied load there, so I can get rid of that. I'm going to put a line feed between these, and then I'm going to say okay. So nothing's changed. Nothing's changed in this because this is the representative statically determinate structure, but it's the exact same problem as we solved before. So we now need to determine how much the node B moves to the right. Okay, what is this displacement with this applied force P? Okay, so because this has got a vertical reaction here, which is FBY, this node has to stay in the same location. It can't move, sorry, this node has to stay in the same vertical position. So the movement here which is big delta, delta Bx, is going to be equal to whatever the change in length of this member is. Equal to delta L of AB. And if we can remember from our beam theory, well, we've got stress is equal to Young's modulus times strain, so that's force divided by cross-sectional area is equal to Young's modulus multiplied by delta L on L. We can rearrange this whole expression to give delta L is equal to F multiplied by L on EA, where F is the tension in the, or the tension applied to a beam member. So that would be applied like this. So for our purposes, this is the little f in inside our structure. So it's going to be the internal forces which we've determined here. Now we don't know what E, A and L are in the problem I gave them to you, but we actually don't need them to determine the internal forces because we can just leave this and we'll end up with the extension of this member is going to be a function of E, A and L. And then what we'll find that the second extension, when we push it back the other way, is also a function of EA and L. So we can determine this. I will just write this down here. Determine the deflection of the structure, which is big delta. I need to make some symbols for E, A, and L. sp.symbols. And then we've got F, so the member that we need is FAB. Okay, so big delta is equal to internal forces AB multiplied by L divided by E multiplied by A. And so we can put down here print, which gives a displacement delta bx equals big delta. Okay, so the displacement is going to be P multiplied by L divided by 2AE on there. Okay, so that's the amount the structure moves to the right. Again, we could have done this whole problem by hand, but I want to show you how to do this, coding this stuff up, and it should become a little bit easier to go through and do this by code. So we've got our big delta now, which means that the structure is moving to the right because it's a positive number. So we now do the whole thing again. We're just going to set the external force to be 0, and we're going to set the known value of bx, which is the redundant force, to be equal to -1, and we're going to see what the little delta is. So the easiest way to do this is to copy this whole bit here. Let's just narrate what I'm doing. I'll say, now we set the redundant reaction Okay, so all of the lines of code that I've got up here, I'm going to copy down here. So set the redundant reaction to be -1. So now I've changed this to -1. The applied load I'm now going to put to 0. Set the applied load to be 0. All of the rest of the codes, all of the rest of the lines should work. I'm just going to change some of the text in here. So I'm going to say, for the representative statically determinate structure with FBX equal to -1 and no applied load. Let's try and run, and we'll change this to little delta. Okay, so we've now got the big delta and the little delta determined here. And then from these, I just divide the big delta by the little delta, and it gives me the value that my redundant reaction must have under the applied load. You probably already see what it's going to be. So now we may determine the redundant reaction. So Fbx is equal to big delta divided by little delta. Which gives a redundant reaction due to the real load of Fbx. Okay, gives us a redundant reaction due to the real load of P on 2. That's fine, I just don't like the syntax of that, but it gives a redundant reaction Okay, so that now tells me what the actual value of Fbx under load P is. It tells me that this is equal to minus P on 2, so it's a force in this direction, which we can hopefully see means that this one must also be minus P on 2, just to maintain equilibrium on the structure. And so when we put the numbers in, and I put this back in and we work everything out, we should get Fax is also equal to minus P on 2. Let's try again. So let's copy the whole thing. Let's just say with the value of Fbx now known, we can determine all of the internal forces in the structure. Then copy all of that code in again. So we'll set the redundant reaction to be the value we've determined. And I called this FBX. Yep. I'm now going to change the applied load to be P again. So we can now change this to be for the real structure. It's real structure with applied load. The reactions are and the internal forces are. Let's get rid of this. Here we go. So as I expected, we've got the reaction at node A is minus P on 2 as well. So these two give us horizontal equilibrium. The internal force in member CB, let's just get my diagram up, check these make sense. Let's use this one. Okay, so it says here the internal force in member CB is minus P in compression, which makes sense. So this one is getting squashed. The internal force in member AB is, this one is 0. So this is a no force member, and that makes sense because this is the force now applied on this is got a force of minus P on 2 in that direction, minus P on 2 in that direction. And if you solve for equilibrium, you'll find that actually the force in this member counteracts that P on 2 there, and the force in this member counteracts that P on 2 there. And I leave that for you guys as a challenge to look for. We find this is actually a 0 force member under this structure. So this is how we go through and how we use the force method for a structure like this. This was relatively simple to do because we were able to see that with this structure, the displacement of the node at which we had the redundant reaction in the direction of the reaction was aligned with the extension of a member, and that's what made it really easy. For even ever so slightly more complicated problems, it becomes quite difficult and cumbersome to determine deflections. And what we're going to use and what this module is designed to introduce you to is to utilize work energy methods where we can determine the external work done, which is just a force multiplied by what's half force multiplied by displacement, and then looking at the internal strain energy stored. So hopefully that's been a good introduction to the force method. We can think the force method is pick a redundant reaction, set it equal to 0, work out how much a structure moves in the direction of that reaction. If it's moved in the direction of that reaction, set it equal to -1, and then work out how much the structure moves back. Take the big displacement divided by the little displacement, and that is your number. Okay? If you found out that it had a negative displacement in the other direction, then set the redundant reaction to be equal to 1, and you'll get the numbers will all come out in the wash. Okay? So in fact, let's just try that. So let's go up here, let's say, okay, in fact, I'm not going to do that. I'm going to leave that as an exercise for you guys to determine. So if the problem had been stated the other way, so it had P here, then we can see that from symmetry, the force has to be P on 2 here and P on 2 here. So the first displacement that you would be solving for is this one here, delta Bx, and you find it was just the same value we had before, but it would have been a negative value. Okay. For this case, we would have then set the force to be equal to this redundant force to be equal to a positive load in this direction, and found out that the little delta would have been equal to a positive value. So we would have then have this negative number divided by the big positive number to give us the real displacement. Okay, so that is how we do the force method. That's how we code it up, and I hope you guys realize that some of this coding stuff might seem like I'm really trying to hammer it down on your throats how to use Python for lots of different things, but if you did this bit by hand, you'd have to do it by hand for each of these systems. So you'd have had to solve this system, this first system. You'd have had to have solved this second system here, and I should highlight those. Let's say and you then would have had to solve this third system as well. Okay, and as problems get more and more complex, we'll have to solve this more and more times as we go through. But hopefully you can see that by a little bit of coding, by saving your free body diagram and your method of joints as some sort of functions up here, and even things that help you, just printing things out, then you can do a lot of what is ultimately handwork much, much faster and more repeatably. So I hope that's been a useful introduction to what the force method is. I think I'd hoped you guys would have covered that by now. Obviously you have not. Go through, if there are any questions, you know where to find me. I'm going to do a more complicated example next, and then we're going to find that actually we can't quite do that complicated example. So we'll then do a slightly simpler one, and then we'll have to introduce the concept of the principle of virtual displacements to solve the really complicated one. So hopefully that's been interesting for you guys. I look forward to seeing you guys in my next few lectures. I find this topic really interesting. Okay, last topic, shear center. It's kind of cool, but this stuff is actually really interesting, and I hope that you guys find it as exciting as I do. So remember, like and subscribe, and have a wonderful weekend, and I'll see you all next week.